Okay, so let us recall that we have been going through the notion of GCD, greatest common divisor. By now we have seen quite a few things about the notion, and in particular among them we have seen the Euclidean algorithm, and that is where we are right now, which is of course a very systematic way of finding the GCD of two given integers, at least one of which is non-zero, so that the GCD exists. Now, parallel to this notion of GCD, you already know that there is another notion, that is least common multiple, LCM of two integers. So next the discussion continues like this. So the author says there is a concept parallel to that of greatest common divisor of two integers, known as their least common multiple, but we shall not have much occasion to make use of it. The reason for that is that LCM and GCD are related, so that if you know the GCD, you automatically know the LCM. Anyway, so let's see what the notion of LCM is all about. Now, before we go to LCM, we need to know CM, common multiple. So that's how we have this next thing. An integer C is said to be a common multiple of two non-zero integers A and B if A and B both divide C. Now, because these divisions are involved, so we need both A and B to be non-zero, unlike the case of greatest common divisor, where at least one of them needs to be non-zero. Now we need both of them to be non-zero. So if this happens, then we call C a common multiple of A and B. Evidently, 0 is always a common multiple of A and B, regardless of what the non-zero integers A and B are, because A and B always divide 0. Any non-zero integer divides 0. Now, to see that there exist non-trivial common multiples, you just note that these two products, AB and its negative minus AB, actually are both common multiples of A and B. Now, because A and B are taken to both be non-zero, so AB and minus AB are both non-zero integers, and because of that, exactly one of them will be a positive integer, right? So that's what you see. These are both common multiples of A and B, and one of these is positive. It has to be positive. So that means we see that if we start with two non-zero integers, A and B, then there exists at least one common multiple of A and B, which is a positive integer. Note one more thing, that A and B themselves need not be positive. In fact, both of them may be negative also. But since we are considering positive common multiple, so at least one of them exists. That much we know. So that means the set of all positive common multiples of A and B is non-empty. And because we are talking about integers, so that means this set of positive common multiples of A and B is a non-empty subset of the set of positive integers, or in other words, natural numbers, if you do not include 0 among them. So that means you can use the well ordering principle here, and by the well ordering principle there would be a smallest such integer, which is a positive common multiple of A and B, and that will be the least common multiple, because positive common multiple among them the least, so least common multiple. So that is the next thing we are going to write, or rather the author has written. So by the well ordering principle, there exists a smallest such positive common multiple of A and B, and that is the least common multiple, which we call, I am of course not exactly writing what Burton has written, but I am writing the same thing in my language, which we call the least common multiple of A and B. And the definite article B is justified because by its very nature it is the least something. Okay, so we don't have A here, it is unique. For given A and B, it is unique, just like GCD is unique, this is also unique. And here next, that same thing is given in the form of a formal definition. This is definition 2.4. The least common multiple of two non-zero integers. Again, I am repeating, don't forget that here both the integers must be non-zero. Okay, if you consider one of them to be 0, then it does not make sense to say LCM of them is this. Of two non-zero integers A and B, and we already know very well the notation denoted by LCM of A and B is the positive integer C satisfying, what is the exact language, is the positive integer M. Okay, let's call it M. M satisfying the following conditions. Condition A, of course, demands that C be a multiple of both A and B, that is A divides, or again I am saying C, M. A divides M and B divides M. And the second one is that among such positive common multiples, M is the smallest. If C is a positive integer such that I think the author has written if C is an integer which is divisible by both and A and B with C greater than 0. Now I am remembering, but anyway it has the same meaning. If C is a positive integer such that A divides C and B divides C, then M is less than or equal to C. M is the least among the positive common multiples of A and B. Next, we are going to take an example to illustrate this notion, but I need ink first. And do you notice one more thing? Just like when we calculate the GCD of two integers A and B, their signs do not matter. They may be positive or negative or anything, any combination of positive or negative. Here also, the LCM of A and B actually does not depend on the signs of A and B. By that, what I mean is this. Say A and B are two non-zero integers. Then you have this, which just follows directly from the definition. LCM of A and B is equal to the LCM of minus A and B, which is equal to the LCM of A and minus B, and that is equal to the LCM of minus A and minus B. And the reason is same, because when we have divisibility relations like this in some definition, not just GCD or LCM, the fact that we are considering the integer in which we are interested to be a positive integer, and the fact that division like this is unaffected by signs, or rather I should say divisibility or lack thereof is unaffected by sign. That's why we have this kind of relations. So what I mean by that is simply this: if A divides M, then minus A also divides M. Similarly, if A does not divide M, then minus A also does not divide M. So that divisibility is unaffected by change of sign or whatever sign it may have, the integer. Okay, so now next we look at this example. As an example, what are the integers? Minus 12 and 30. The positive, just to emphasize this fact that one of them can be minus, the other may be plus. They are taking minus 12 and 30. The positive common multiples of minus 12 and 30 are 60, then 120, then next 180, and it will of course not end, because common multiples will get larger and larger, and in fact if you multiply a common multiple by any integer, you get another common multiple naturally. For example, here you multiply this common multiple by 2, you get another larger common multiple. So it will continue to go just like this without any bound. Whence we have LCM of minus 12 and 30 equal to 60. This part is left to you. You convince yourself that these are in fact the positive common multiples and the least one is 60. The following remark is also clear. Given two non-zero integers A and B, their least common multiple exists, and we clearly have this relation that the LCM of A and B is less than or equal to this, which is coming from where in fact, because we have already seen that AB is a common multiple of A and B, and in fact minus AB is also a common multiple of A and B. Among them, the positive one is one of them will be positive and the other will be negative because they are both non-zero, so their product is non-zero. Among them, the positive will be a positive common multiple. So that one of course will be the absolute value of AB. If AB is positive, this is equal to AB. If AB is negative, then this absolute value is equal to minus AB. So that means this is an integer which is a positive common multiple, and LCM of A and B by definition is the smallest such positive common multiple. So that's why we have this inequality. Now, do you note one more thing about the relationship between LCM and GCD in this sense? There is of course one relationship, exact relationship, which will help us calculate the LCM if we know the GCD, but even before that, I want to draw your attention to this fact. Say you have two integers A and B. Now we are going back to the notion of GCD for a moment, at least one of which is non-zero. Then we have the definition of GCD. Okay, GCD is a positive integer D which has to divide both A and B, and if there is a positive integer, say x, which again just like D divides both A and B, then x is less than or equal to d. Such a positive integer d is called the GCD of a and b. Now from this definition and from the fact that at least one of these is non-zero, it is not immediately obvious that d actually exists. In fact, that is our result which we have already gone through, that if a and b are at least one of them is non-zero, then their GCD in fact exists, and it can be written as a linear combination of a and b, where lambda and mu are positive, integers. And this is a non-trivial fact. It's not at all immediately obvious that this is the case. However, from the definition of an LCM of two non-zero integers, and from our discussion even before we wrote the formal definition down, we can pretty much almost see without much effort that the LCM of two non-zero integers actually exists. Because unlike the GCD case, here the things are much easier. You have, just to repeat that discussion again quickly, if you have a and b, two non-zero integers, then this is a positive common divisor of a and b. That is why the set of positive common divisors of a and b is a non-empty subset of the set of all positive integers. So by the well ordering principle, there is the smallest element, and that smallest element by definition is the LCM. So it is much easier than the existence of GCD. Okay, so that thing is there, that difference between the existences of these two things. The GCD, the notion of GCD is a little confusing in this respect. Do you see how? On one hand, we are saying that D is the greatest common divisor. It's the greatest among all common divisors. On the other hand, if you go back to the proof of this, you will see that there we started the proof of by considering a set which looks like this, where x and y are integers. Using the fact that a and b, at least one of them is non-zero, we first showed that s has a positive integer, and then of course again we used the well ordering principle, and that allows us to conclude that this set, the subset of this set consisting of the positive elements has a smallest element d, and that smallest element then we show turns out to be the GCD of a and b. So on one hand we are saying that it's the greatest of something, but in the proof we are getting it as the least element of some set. Okay, so do not confuse yourself in these two things. It is the greatest among the set of all common divisors, but it turns out to be the least elements of some other set. Okay, so now finally we come to this relationship between GCD and LCM. Let A and B be two positive integers. then now see, because both A and B are positive, that means at least one of them, in fact both of them are non-zero. So by our previous result, their GCD exists. That is the first thing. The second thing is that because both of them are non-zero, LCM also exists, and we have a relation like this. Then their GCD times their LCM is equal to their product. Okay, so this is the relationship between GCD and LCM. And let me emphasize one more thing, which we at first we may neglect or forget. A and B both have to be positive integers, okay, for this to happen. Now the proof. Let D be the GCD of A and B. Now because D is the greatest common divisor of A and B, that means D actually divides both A and B. So that means A and B will be multiples of D. So we can express them like this. Let A equal to D, say dx, and B equal to dy, where x comma y are positive integers. Just simply the fact that D divides A and D divides B would not necessarily imply that these x and y are positive. However, here we will have positivity because A and B are both given to be positive and D by definition is positive. So x and y both have to be positive. Also, we know that this relationship, so that also we will have to use it. So let's just write that. Also, D is equal to, let's take that one itself, A lambda plus B mu. Lambda and mu, however, need not be positive or anything like that. They are just integers. For some integers lambda and mu. Okay, so now next what we do, let us consider this quantity M to be AB divided by D. Okay, so we have multiplied A and B and we are dividing that integer by D, and that quotient we are calling M. Now first of all we need to see that M itself is actually an integer. Note that however, we will not just simply write M is an integer, we will write much more than that. Note one thing from here, A is dx, so A divided by d would be x, so that means m is xb. And just like that, because b is dy, so b divided by d is y, so this is equal to ya, i.e. m is a common multiple of A and B. Also, M is positive. M is a common multiple of A and B because we have realized M as a multiple of B here, and that is because x is an integer, and in fact x is positive also, although the positivity here does not play any role. So M is a multiple of B, just like that M is a multiple of A also, an integer multiple, because Y is an integer. At the same time, M itself is positive, and that positivity of M is coming from its very definition. A, B, D, all of these are positive, so naturally M is also positive. So M is a positive common multiple of A and B. Our aim, of course, you can guess, is to prove that M is the least such. It is in fact the LCM. So to show that, let us consider any positive common multiple. What shall we take? Let us take Z. Let this be a positive common multiple of A and B. Let us also write, those relations involving Z, A and B. Let Z be equal to A alpha equal to B beta. I'm not sure, I don't remember whether we will need this or not, but we will see, where these are positive integers. A and B are positives, that is taken to be positive, so alpha and beta will also be positive. Okay, now look at this, Z divided by M. Z divided by M is what? Z is, okay, but before we do anything to Z, let's just for a moment keep Z as it is and use M. So we will have Z D divided by AB. Now we use that relation. D is expressible as a linear combination of A and B. Specifically, we have taken D to be equal to A lambda plus B mu divided by AB. Okay, so now this becomes equal to You see, if we perform the division means if we distribute AB to these two terms, then in the first term A and A cancel out, we are left with Z divided by B times lambda. In the second term B and B cancel out and we are left with Z divided by A times mu, and that becomes equal to, because of these extra relations, okay, so first we have Z divided by B, so that means this is beta lambda plus Z divided by A is alpha mu. Note that this is a positive integer. Why? Because this is equal to Z divided by M. M is positive, we have already seen that, and Z we have taken it to be a positive common multiple of A and B. So that's why this has to be positive, and because you can see that here all the quantities are integers, beta, lambda, alpha, mu, so this combination is also an integer. This is a positive integer. Hence, because this is a positive integer, its least value is 1, so this is greater than or equal to 1, which implies that Z is greater than or equal to M. So not only have we shown that M is a positive common multiple of A and B, but we have proved that any positive common multiple of A and B, if we choose Z, then M cannot exceed that. So that means M is the smallest positive common multiple. So M is the least common multiple. So M is equal to LCM of A and B, and we have equal to AB divided by D, which is equal to AB divided by D is the GCD of A and B, and that's just it. You multiply on both sides by GCD of A and B and you get the exact equation that we have in the statement of this theorem. So I end the proof here itself. Now there is a corollary to this, a special case, which is also worth mentioning. If A and B are two relatively prime A and B are still positive because we want this to be a corollary to that theorem. But now additionally A and B are relatively prime, that is their GCD is 1. positive integers, then we have the LCM of A and B equal to the product of A and B. So this is one very special case in which it's almost instant. I mean, you can instantly calculate the LCM. You just take their product and that's it. That is the LCM. Next, continuing our discussion, but wait, give me a moment. Perhaps the chief virtue of this theorem, I have already forgotten the number, 2, 8, is that it makes the notion or calculation, notion of GCD or notion of LCM, calculation. Oh, I'm seeing things. I looked at some other part. It makes the calculation of the least common multiple of two non-zero integers dependent on their greatest common divisor. So that's what we were saying back then, that LCM in fact is it depends completely on the GCD, and if we know the GCD, we know the LCM. And the GCD itself can be calculated using the Euclidean algorithm in turn. So that means actually you can say that there is also an algorithm for calculating the LCM of two non-zero integers A and B. So first you apply the Euclidean algorithm to calculate their GCD. Then in your next step you use this theorem, and with the GCD value you then calculate the LCM. Can be using the Euclidean algorithm. Euclidean algorithm is so nice, huh? I mean, we don't often come across this type of absolutely mechanical rules based on which you can in fact write a computer program, and that's why this is called an algorithm in the first place. You don't even have to think of anything, you just mechanically you keep on dividing and dividing until you get a zero remainder. The first non-zero remainder is your GCD. When considering the positive integers, now this is, we are going to mention another example which we have already seen. The values will remind you of that. Considering the positive integers 3054 and 12378, we already saw that its greatest common divisor is 6. For instance, hence by our theorem we have this. Times now while writing I'm digressing, okay, I'm going to talk about something else. While actually writing, whether or on board or on paper, it is difficult to always maintain things and write things neatly, but at least you maintain this, that when you put a dot to denote multiplication, you try to put it in the middle, okay, and if you want to mean decimal point, you put it at the bottom. Here we mean multiplication, so we put it in the middle, and this turns out to be equal to this value, so that value will be the LCM. And that value equals what? 6300402 or 402. So that is the LCM of these two integers, 3054 and 12378. Before moving on to other matters, we observe next that the notion of GCD can be very naturally extended to more than 2 integers, in fact any finite number of integers. So that is the next thing. Before moving on to other matters, we note that, or let us observe the same thing. that the notion of greatest common divisor can be extended to more than two integers, and the case where we have three integers is of course this. In the case of three integers, A, B and C we define their greatest common divisor, denoted like this, to be again the smallest positive divisor of A, B and C. For a moment I confused myself. I was writing about GCD, but in my mind I was thinking of LCM. I forgot that the LCM thing is already over. So it's again we are talking about GCD. So just like the ordinary definition of GCD, this also, I mean similarly we just have one more integer than usual, than our usual two integers. Having the following properties, D is a divisor of, so it has been written by the author as a formal definition. Same thing, whatever I have said, I have written here, he is writing in the form of two conditions. What he writes is this: define GCD of ABC to be a positive integer satisfying these two conditions, that it divides A, B and C, and if you have any other positive common divisor of A, B and C, all three of them, then that thing, say that is E divides A, B and C and E is positive, then this integer has to be greater than or equal to E, that is it's the greatest among all positive common divisors. In fact, we don't need to consider positivity of the other common divisors because the negatives will anyway lie on that side. We cite two examples of this extended definition. One of them is this: GCD of 39, 42 and 54 turns out to be equal to 3. That is one thing. And GCD of 49, 210 and 350 turns out to be equal to 7. don't make the mistake of only considering any two of the integers. Say you, in a frenzy of calculating things, say you encounter this kind of GCD somewhere in the middle of a very big calculation. In the back of your mind, you have your usual GCD. So while quickly calculating things, you entirely ignore, you disregard this 350 and you end up calculating the GCD of only these two. That may be a different answer, okay, and that anyway is not this GCD, because you be careful about that. The reader is cautioned, and the author then next is cautioning us about something else. That it is possible for three integers to be relatively all that thing. That it is possible for three integers to be relatively prime when this GCD is 1, but any two of them are not relatively prime. The situation is somewhat like considering the intersection of three sets. The intersection of three sets may be empty. However, if you take any two of them, that intersection may not be empty. Okay, they may not be mutually disjoint, but the intersection of all three of them is the empty set. So the situation here is somewhat like that. Possible for three integers to be relatively prime as a triple. That is if A, B and C are the integers, this is what we mean by this, that they are relatively prime as a triple, but no two of them are relatively prime in the usual sense. And one example, of course, is this. For instance, GCD of 6, 10 and 15 is 1. 1 is the only positive integer that divides all these three simultaneously. However, GCD of 6 and 10 of course is 2. It's not 1. GCD of 10 and 15 is 5, and GCD of 6 and 15 is 3. From these GCDs, actually you can see how the author came up with these integers. What he did is that he took three distinct primes and then taken their products by taking two at a time. So that will create this situation. Okay, so now this ends this section. I mean the theoretical part of this section. Next we look at the exercises, where of course I will just simply start the exercises and then we will solve them gradually through the course of the next few videos. In this video we will solve the first one. So this is exercises 2-3. The third section of the second chapter. We have only gotten so far because we are doing many things simultaneously, groups, then vector spaces, rings of course we have already done, field theory, what else, graph theory also we are doing, calculus also we are doing. So it takes time to again come back to the same videos. That's why this delay. So the first one is nothing new. It asks us to calculate the GCD of two integers using of course the Euclidean algorithm, because that's what we have now. Find the GCD of 143 and 227, that is one. Then next, the GCD of 306 and 657, and the GCD of 272 and 1479. So you already know the procedure. You have to apply the division algorithm again and again in a specific manner. Let's go through the calculation for this one first. We have, so the larger one is 227. We divide that by the smaller one, 143. In this case, the remainder, I am not dumb enough to actually do the calculation here itself. It will take a very long time, given also the fact that how well I can do calculations. So I have the things done here for me. So I am just going to simply write them down. And you need to understand what we are doing. Here we have divided 227 by 143. The quotient is 1 and the remainder is 84. The next we divide the previous divisor by the previous remainder. So 143 we are dividing by 84. So in this case the quotient again is 1 and the remainder is 59. And the calculation goes on like this. Next, 84 equals 59 plus 25. Next, I can in fact write here one more equation. 59. This at least we can see what it will be. 2 times 25 is 50. 50 plus 9 is 59. 9 is of course less than 25 and it's a positive integer also. Then So this is what? 7. Next it becomes trivial. 3 times 2 plus 1, and 2 of course is 2 times 1 plus 0. Once you hit 1, you can just stop there itself. The algorithm, however, demands that we write one more step because we need to reach 0 integer. Hence, by the Euclidean algorithm, you write those things. We directly write GCD of 143 and 227 is equal to 1. There is a shorter way of calculating this GCD. If you notice one thing, you see there is another way of calculating the GCD of an integer which does not involve using the Euclidean algorithm, which instead depends on the prime factorizations of the given integers. Now you don't really need to know the prime factorizations of both the integers, at least in this case. Do you notice one thing, that 143, at least this much I know, despite the fact that I am very bad at calculating, that 143 is 13 times 11. Now this is the prime factorization of 143 because 13 and 11 are both primes, and then you verify the fact that none of these two primes divides 227. So there is no common prime factor, and that is why the only positive common divisor can be 1. So if you recognize this fact, you can just immediately write 1. But because all these things are happening at the end of this section, which involves the Euclidean algorithm, so we have decided to use the Euclidean algorithm. And this method, however, will not always work, because in general these are very small integers, right? They are insignificant in terms of calculation wise. I mean, in terms of calculation, I am saying these are not really significant. If you encounter very large integers, I think this aspect I mentioned before also, if you have two extremely large integers, then going through the Euclidean algorithm to find their GCD is of course a systematic process which involves only divisions. However, finding their factorization is a very difficult job. Much more difficult than going through the hassle of using Euclidean algorithm. Maybe there are many divisions involved. However, finding a complete factorization of a given arbitrary positive integer is in fact a very difficult task, and the reason that it's a difficult task, it of course lies in the fact that you have to find the prime factors, and the fact that this is so difficult in fact makes cryptography possible, which is based on the difficulty of factorization. So in this case we have been able to get things done like this just by observing this, if one wants to write the solution using this method, but it is completely ad hoc. It may not work in any other case. And the other two I will not do, I am leaving that to you. You please go through the calculations, and I will however write the answer. (306) and 657 turns out to be equal to, what was it, 9 I think, yes. And this still larger one this turns out to be equal to 17. So you please complete these calculations, and then in the next video, next Burton video, we are going to see the other solutions to the subsequent exercises. So with that, I am ending this video. If you want to say something, you can write in the comment section below, or you can mail me at my usual address, which will be, the link will be there in the description. And that's just it. So we have again gone through number theory. So today is Tuesday, this coming Friday we will see again graph theory. So that being said, see you on Friday with graph theory once more. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.